Modeling human movements is important for physical human-robot interaction. In particular, the range of human joints needs to be modeled accurately in order to design a robot that can interact with humans safely and effectively. Existing physics simulators allow us to specify the upper and lower bounds, that is, to set box constraints for each joint. The constraints are then enforced by computing and applying the so-called constraint forces. However, human joint limits are dependent on the poses of other joints. Take our arms, for example. We can bend our elbow to almost 180 degrees when the arm is beside the torso, but when the arm is behind the torso, the range of the elbow joint is much smaller. Acton and Black in their 2015 paper collected a dataset of humans performing various stretching poses. Based on that, they proposed a validity procedure. Given a human pose, this procedure will evaluate whether the pose is feasible or not for humans. However, we cannot directly use this procedure to enforce joint limits in a physics simulator, because the calculation of constraint force requires the gradient or Jacobian of the constraint. As you can see, there are many if statements and table lookups in the validity procedure proposed by Actor and Black. We need to make that differentiable. Given a joint configuration Q, we propose to learn a neural net function C of Q such that if CQ is greater than 0, Q is a human valid pose, otherwise Q is invalid. C is thus differentiable, and its gradient can be efficiently obtained through backpropagation. We simply call the validity procedure by Actor and Black to label our training data. By enforcing our pose-dependent joint limits in the simulation, human-like behaviors emerge even without any internal control forces. Imagine the arm of an astronaut is being pulled in outer space with no gravity. On the left, with our data-driven constraints, the simulator will only produce feasible human poses under the law of physics. On the right, using default box constraints produce clearly infeasible poses. Here we see a human passively falling onto the ground under gravity. On the left, with our pose-dependent joint limits, the motion looks more natural. We can also use our learned CQ and its gradient in solving IK problems. On the right, without the data-driven joint constraint, the naive IK solver reaches the target with a clearly unfeasible pose. Instead, with our method, the solver correctly fails to reach the target. Finally, a bonus of using our method is that self-penetration is automatically mitigated. This is simply because a valid pose within human range of motion will not be one that is self-penetrating.